All right, so we'll get through some of the Alex topics today, and then we'll try to finish up in the next 2 class periods, chapter 3. So these are what we're trying to get through today. Let's go back here. So the first thing is Lewis dot diagrams for an element. So all we do is we write the symbol, and then we need to write how many valence electrons are around the element. So if we look at rubidium, this is from chapter 2. So we're taking what we know. How many valence electrons around rubidium? Good, it's 1. So we just turn on our pen tool. We're just going to draw a dot by rubidium. Okay. So each element, you can imagine that we have a box. Each side of the box can fit 2 electrons. Okay. So rubidium has 1 valence electron. We're just going to show the valence electrons. We're modeling the valence electrons. Rubidium has 4?
Yeah.
Okay. So I'm gonna put 1 on each side because this is gonna model how our electrons bond. How about iodine?
5, 6, 7.
7. Okay, I'm gonna put them like this. 2, 4, 6, 7. And krypton.
8.
So we're just gonna fill all of the sides with electrons. Okay, so those are our Lewis dot diagrams for our elements. We just have to figure out how many valence electrons and draw them around.
Oh, you just draw them around?
It kind of does, yes, kind of. So I like this box. So I like to draw, if there's just 2, I will draw them together. But you probably, I think the best way would just be like 1.
I have it because it's like, it's this one. Yeah.
I would do like
this
that.
Weird box from last year where it was like 1, 2, 3, 4, 5. I don't know, actually, it might have been just like whatever.
Okay, yeah.
Weird.
So I would probably just go around once and then go back around.
Okay.
Does that make sense?
Yeah.
Yeah. Okay, we don't draw the box though.
No.
Okay. All right, so we are going to talk about the octet rule. The octet rule comes from this fact that all of our atoms want to have 8 electrons in their valence shell. Okay, if we have 8 electrons in a valence shell, that's a more stable set of electrons, and that's what drives things in chemistry. If it can be lower energy, then it's going to want to do that. Okay, so lower energy drives these things. So this is for the S and P block. We'll look at what that means. So atoms are going to gain, lose, or steal electrons so that they can have 8 valence electrons. So we have this like golden number of 8 electrons, and atoms will either take electrons, or they'll donate electrons, or they'll share electrons so that they will have this more stable conformation of 8 electrons. Questions on that?
How would you lose?
We will look at that one. They just give them away. We'll look. Yeah. Good point. Good question. So this is our periodic table. We've seen this before. This is the S block. This is where our S orbitals are filling. This is the P block. This is where the P orbitals are filling. So anything in these regions is going to follow the octet rule. They're going to want to have 8 electrons or lose electrons, so they have 8 electrons. Okay. Sorry? Okay, so we can use this fact that everything wants 8 electrons. It wants a full shell to decide if it's going to be a cation or an anion. Okay, so if it's losing electrons, will it be a cation or an anion? Cation. If we lose electrons, it's going to be more positive. If we gain electrons, it'll be an anion. So we're looking at group 1 elements. That's that first column. So how many valence electrons does the first column have?
1.
Good, 1. They have 1 valence electron. So we can look, they're either going to want to gain 7 electrons, or we could just get rid of this outer electron, and then the inner shell will have 8 electrons. So are these ones going to want to gain 7 or lose 1? That's easier. They're going to lose 7 electrons to achieve, 1. There we go. Let's fix it. They need to lose 1 electron to achieve an octet. So they're just going to get rid of their valence electron, the outermost ring. And then, if you lose 1 electron, what will your charge be?
Negative.
Plus 1.
Yep, do that.
Okay, does that make sense? So the first column, generally they're going to be plus 1 because they're going to lose 1 electron so that they can have an octet or a full shell. Okay, let's try another one. So group 15, this is arsenic, phosphorus, nitrogen. So how many valence electrons do they have?
5.
They have 5 valence electrons. So what do you think they're going to do? Are they going to lose 5 so they have a full shell? Or are they going to gain 3?
Gain 3.
Good. They're going to gain 3 electrons. So what will their charge be?
3
Negative
minus
3.
3.
Good. 3 minus 3 charge because they are going to gain 3 electrons. Okay, questions on that? Does that make sense? So that all of the groups follow this pattern. We can figure out that. Okay, the tricky one is the carbons column, group 14, carbon, silicon, germanium. How many valence electrons do they have? Good, they have 4 valence electrons. So they are kind of weird. They're going to either gain or lose 4 electrons to achieve an octet, because they're right in the middle. They're halfway between having 8 by gaining or losing. And so they're going to be either, if they gain electrons, they'll be minus 4. If they lose electrons, they're going to be plus 4. They're kind of in the middle. Generally, this group doesn't gain or lose that many electrons. They don't usually do this. Okay, but if they become a cation or anion, they could be either plus 4 or minus 4, based on the octet rule. Okay, this is the last group. Group 18 is the noble gases, those ones up there that are in light blue. So they all have how many valence electrons? You said 3 valence.
8.
Good. They have 8 valence electrons. So they have achieved an octet. Let's put already. Oops. They already have an octet. They don't form ions. Do not. This is not going to work to erase. Let's try it. Okay. So because they have a full shell, that's what explains the stability of noble gases. They have their octet, that's really stable, that's a really low energy conformation. So they're not going to need to gain or lose or steal electrons. They're just stable. So they don't usually form compounds. They don't usually react. Okay, questions about that? And that can be explained based on our octet rule. Okay, so I think we talked about this in the last chapter, but I realized it should go here. So I'm going to bring it up again. So these are all ions that have the same charge all the time. So the first column always forms plus 1 charge. The second column always forms plus 2 charge. There's a few transition metals. Silver is always plus 1. Cadmium and zinc are always plus 2. The third column after the transition metals are always plus 3. And then we skipped carbon here, right, because it's kind of in the between. It can be plus or minus 4. And then we go back to our nonmetals, and our nonmetals are going to form anions. And we've got 3 minus, then 2 minus, then 1 minus. Okay, and then the last column, they don't form ions. Okay, questions on that? And this is explained by that octet rule. Okay. Do we need this for a minute? Looks like people are waiting. Yes, Stockton.
So, on like the plus 3, why doesn't like the boron have a plus 3?
Good question. So boron is kind of like carbon. So boron is a metalloid, and they generally don't form ions. They usually do what we're going to talk about in chapter 4. They do covalent bonding.
Oh.
And so they're going to share electrons. So if you're forming an ion, that means you're going to give an electron or take an electron. So those ones give electrons, these ones take electrons. Boron, carbon, silicon, germanium, generally they're going to share electrons. They're not going to just give away their electrons. Yeah, good question. Okay, other questions? Yeah, Phil.
When you're an ion, are you usually in an ionic bond?
Yes.
Ion?
Yes. Good. Yeah, usually. Okay. All right. We need to talk about this because this is an Alex topic. Isoelectronic is when you have the same number of electrons. Iso just means the same. So, have you heard of iso in any other classes? Isosceles, have you heard that one?
Yeah.
So that's where you have two of the same sides. Iso just means the same. So when we're talking about isoelectronic, that means we have the same number of electrons. So if we look at this example down here, all of these atoms or cations or anions have the same number of electrons. So if we look at argon on the periodic table is in the noble gases. It has 18 electrons. And then we just can move away from argon, and if we move left, we have chlorine. And chlorine has 17 protons, but if we add one more electron, then we have 18 electrons. And then if we move one more away from chlorine to sulfur, sulfur has 16 protons. If it's neutral, it has 16 electrons, but if we add 2 electrons, then it also has 18 electrons. Does that make sense? Okay, then let's go back the other way. So we're at argon. If we move forward and come back around to potassium, potassium has 19 protons. It would have 19 electrons. If it's neutral, so if we subtract 1 electron, that's 18 electrons. And then calcium has 20 protons. It would have 20 electrons if it's neutral. So we're going to subtract off 2 electrons, and it also has 18 electrons. So all of these have the same number of electrons. And I think if you use the periodic table as a tool to move, that's helpful for this second problem. Okay, I want you guys to try at least the top one. If you get done, you can try the next one. So go ahead and find 2 cations and 2 anions that have the same number of electrons as krypton. If you get done, you can do the next one. You need like a minute. Oh, krypton is a noble gas. It has atomic number 36.
One has 36 too. Oh, I guess we're always thinking out.
Okay. So far.
Do one negative.
I can't remember the last time I used like a.
So,
Yeah.
so that would be, yeah, so it would be. But the lower
Yeah, so krypton's gonna be 6.
and then what about bromine? Would that just be?
I think you just has one, right?
You do?
Yeah.
So it's krypton's 36,
Uh-huh.
and then 37 would be RB. That would be a cation.
Good. So you have to do RB what?
But it would be an RB plus.
RB plus. It would be a cation. RB plus because it needs 1 less electron than it has protons. So more protons, more mass.
But you can.
Right.
Okay. Two animals are. Okay.
Yeah, that fits us. Yeah, that is tricky.
Whatever that is.
So,
Yeah, no.
Yeah.
Okay, let's do Krypton. I think we're mostly through that. So Krypton has how many electrons if it's neutral? 36. Good, thanks. So let's do, what should we do? On this side, should we do cations on this side? So tell me two cations that match Krypton.
RB
RB plus and then.
RB plus,
and SR2.
SR 2 plus. Do we agree with that? Whoa. It's playing my recording. Sorry. I don't know why it's doing that. Okay, how about let's go to anions. Yes.
On the first one, what did their
Krypton?
bromine be there too, or no?
Rubidium.
yeah, so that'll be.
Okay, bromine.
That would just be negative.
Yep, bromine has 35 protons. If it's neutral, it has 35, but we need one more, so we're gonna add one more electron.
Okay, got it.
Yep.
Calcium minus 16.
Okay. Calcium minus 16. So you just say calcium is 20, and we add 16 more electrons, and that would work. I tried this in Alex, and I don't know at what point, but at some point it doesn't like that. So I would probably stick to close by. It'll let you get away with a few away from the element. But I tried one that was making me do argon, and I tried to do neon plus 8, or yeah, 8 minus, and it was not happy. So just be careful about how far you go away from the element. But that's true. That would also be isoelectronic. That is true. Okay, questions on that? Okay. All right, so this is where we get, I think, maybe Phil asked us. For an ionic bond, we have a transfer of an electron. So one or more valence electrons moves from a metal to a non-metal, and we get out a salt. So the salt that we're most familiar with is table salt. This is how sodium and chloride are bonded together. So the sodium is our metal. It's in that first column. It gives away one electron to chlorine. So then sodium has 8 valence electrons, sodium plus, and then chlorine now also has 8 valence electrons, and then one is positively charged, one is negatively charged, and then that electrostatic charge interaction is what makes them bond together. So that's an ionic bond. Okay. So when we are looking for an ionic bond, one thing that we should look for is there a positive and a negative charge thing? So something needs to be positive, something needs to be negative. The other thing that we like to look for is there a metal and a non-metal? That's a good indication that it's an ionic bond. So if we have an ionic compound, we have a bond between a metal and a non-metal. The metal is losing the electron, and the non-metal is gaining the electron. So remember on Alex, the periodic table in Alex has the elements labeled. It has metals, metalloids, and non-metals. So if you have something that's a metal bonded to a non-metal, that is going to be an ionic compound. So I would use that periodic table for this type of question on Alex. Okay, so here are some examples of ionic compounds. So that we've got table salt. We have the metal is forming a cation, the nonmetal is forming an anion, and then that charge balance is what's bonding them together. Here we have calcium and iodine. Here is tin and chlorine, and then calcium and phosphorus. So we always have a metal and a nonmetal that are bonded together because they're charged.
Like, do we have to figure out names in this unit?
Yes. Yep, we're going to talk about that next time.
We're going to do like sodium chloride.
Yep.
And have to remember those dumb names like tetra chloride.
Yes. Yep. That's covalent bonding though,
Okay.
in chapter 4.
Oh.
So don't say tetra in this chapter.
Okay.
Yep.
But we will have to do like chloride
Uh-huh.
and have to figure out.
Yep.
Okay.
Yep.
Yeah.
Yep. So exciting, right?
Yeah.
Yes.
No.
We'll know what those chemical names mean. You'll be able to read all of your food labels.
So that would be like sodium chloride or something. Or so it's like
Yeah.
sodium and chlorine. So like chlorine.
Yep. Yeah, so
And
new
that would
chloride,
be
yep.
like calcium and iodine. I don't know what it is.
Okay, yeah, and we'll talk about that next time. All right, so here are some physical properties of ionic compounds. So just think of like table salt. That's the one we're most familiar with, probably. Ionic compounds are crystalline. That means that these they have really, really well-ordered patterns of these positive and negatively charged ions, and they are arranged in some kind of crystal. So this is what sodium chloride would look like. You can also have more complicated arrangements, but we are not getting into that in this class. If you add them to water, then they separate. So you get positive things floating around and negative things floating around. Yes.
Do we need to write this down?
So up to you. Do you think that you'll remember properties? Okay, notes are up to you. So I don't want to say you should write it down or not. So in water, they separate into cations and anions. So we've got our sodium cation and our chlorine anion floating around. They separate from their beautiful crystal structure if they're in water. And because we have these positive things in water, that makes the electrons able to hop through the solution, and that increases the conductivity of the solution. So if you put salt in water and then you test the conductivity, it'll go up. They also have high melting points and high boiling points. Have you guys heard of a salt concentrator? There's like a power plant where they put salt in a big container, and then they use a whole bunch of mirrors, and then they heat up salt. Have you seen that? Okay, and that's a way to store energy through the day because we have the sun. It's called a solar concentrator. And one way to store that energy from the sun is to heat up salt. It takes a lot of energy to melt salt, then they have this molten salt, and then they can use that energy at night to generate power. So that's kind of an interesting thing that they can use high temperature of salt for, of melting salt. Okay. So in chapter 4, we're going to talk more about covalent bonds, but we need to know a little bit about covalent bonds so that we can separate ionic and covalent bonding. So in a covalent bond, the nonmetals are going to share electrons. So the big difference between ionic and covalent is that in a covalent bond, nothing has a charge, and they are all nonmetals. Okay? So remember, nonmetals are up the upper right corner of our periodic table. The other thing that this could be is a metalloid. The metalloids are included in covalent bonding. Remember, they don't really like to form charges. So metals never participate in covalent bonding. Okay. So if we have a metal, then that's going to be ionic. If we have anything that is a charge, that's also going to be ionic. If we have only nonmetals, nothing is charged, that's going to be covalent. talk more about this in chapter 4. We just are kind of getting a glimpse of it so we can see that when we see it on our homework. Questions so far? Doing all right? Okay. Okay, yeah. The other thing to note is, I think I said that, but metalloids and nonmetals can be, that is covalent. It's not ionic. If it's a metalloid and a nonmetal, that will be a covalent bond, not ionic. So they try to trick you with that. So watch out for that. Yeah.
Which one is stronger out of the two? Like between ionic and.
Yep. That is a tricky question because if you take a crystal of salt and you hit it with a hammer, it will break. But if you take like a piece of plastic, which is covalent bonding, and you hit it with a hammer, or like an eraser, then that doesn't break. But you can also measure like bond strength other ways, and usually people say ionic is stronger because it has a really high melting point. If you melt, you can melt plastic at a really low melting point. That's like, so it depends on how you're thinking about the strength of the bond. That would be my answer. I don't know if that answers your question. Okay, other questions, thoughts, concerns? Okay. So in chapter 4, we're going to use our Lewis dot diagrams. So fluorine has 7 valence electrons. And then if we combine these Lewis dot diagrams, so this one's going to give one of its electrons here. They're going to share their electrons. So then if we look at our Lewis dot diagram, okay, are we ready? I'll wait till you're ready. Okay. So if they share their electrons, then they both have 8 valence electrons. Yes, Phil.
Wait, so that's just 2 different ways to show.
Yeah, this is 2 different ways to show that their electrons are bonding. Yep. Okay. And hydrogen is really small, so it only has 2 valence electrons. It only wants 2 valence electrons. So if they both share 1, then their outer shell will be full. Okay. So if we have unpaired electrons in those Lewis dot diagrams, that's where we can show this bonding. Okay. All right. So this is how you should think of covalent bonds. Do you have a joke about covalent bonds? Do share, because covalent bonding is sharing electrons. Okay. All right. Go ahead and look through this list. I'm gonna give you just a minute. See if you can decide if these are ionic or molecular. So that's what Alex calls them. I think of it as covalent, but Alex is going to use the word molecular or covalent.
So ionic.
So the first one I chose no ionic. It's NA.
Is an ion.
I forgot what NA is. It has to ionic complement. So I think it's just molecular. I think it's ionic. Sodium or weight? What is Na? Sodium is a metal. You're saying that Na is
We don't use it.
and why? That is non-metal.
Oh, okay, yeah.
Yeah, that would be great. I can't think where I can't find it. This should be Na. Okay. I forgot about that.
No, actually,
That is
Ionic.
molecular is another way to say covalent.
Oh,
Yes.
that is indeed ionic. AL, that's like a metal, right? It is aluminum.
Okay, it's okay if you don't finish the list. I'll give you a few more seconds, and then we'll go through it.
Coffee.
So.
Yards. Yard. Okay, CO2 is that is molecular. And CH4 is definitely molecular.
All right, let's go ahead and look at these together. Remember, practice in Alex is probably more important than practice during class. So let's go through a few of these. I want to highlight this one. What do you guys think about this one down here? So this one is the trick one. This is the trick one. It's a metalloid and a non-metal. This is molecular. Okay, so if it's a metalloid and a non-metal, that's going to be molecular or covalent. Okay, all right. How about this one? Good. This is molecular. Okay, I'm just gonna abbreviate. How about this one? Good. This is ionic. Okay. Are there any others up here that you want to go over that you were stuck on or confused about? Should we do one more? How about this one? Good, this one's ionic. Okay. Let's go to the next slide. Oops, I wrote on the... Okay. So, I'm going to give you a list of polyatomic ions. Alex will not have these on the test, but it's going to ask you about them. So you have to memorize these or write them on your note card.
All of them?
Yes.
Bro, write them on my note card.
This list is from Alex.
My instant reaction.
But this will not, you won't have access to this on the test. So you either have to memorize it. Oh. Sorry. So you either have to memorize that or write it on your note card. Okay. So polyatomic ions are pretty common. They're just charged groups of ions. And we find them in a lot of different household goods. So probably the most common is sodium bicarbonate, which is baking soda. Okay, hopefully that's baking soda. Some other ones that are interesting are magnesium hydroxide. That's like in the Pepto-Bismol. That's something that. Yes. Yep. So these are all things from our house that have polyatomic ions in them. Okay. All right. So the trick here is, if it has a polyatomic ion and a metal, then that's going to be ionic. If it's two polyatomic ions, then that's also going to be ionic. Yes.
Is it?
It is. Why? What?
Wait, did you go back to the other?
Oh yes, I just put this one. This one's from like the internet. So this one groups them. This one groups them by element, but these are not from Alex. This one is from Alex. This is the one Alex wants you to know. Okay, so go ahead and look through. Decide if this is a molecular or covalent, or if it's ionic. So if it's charged, it's going to be ionic. If it has a polyatomic ion, it's an ionic.
Cu.
and Cu copper, so that'd be metal copper.
I think PO is phosphorus, oxygen.
Yeah, it should be ionic. So that'd be ionic or ionic, right? PO. But what would be not doing
It's not. If you see one like this, that's actually formula. Then CHNO is AO2CO3, that's no. Oh yeah, leave it alone. Ca, calcium. Calcium is ionic earth metal. Alkaline earth metal, so it would be. Wait, hold up. Go back to CaSO.
I'm gonna give you 20 more seconds.
That's ionic, that's what we were talking about.
Oh, okay.
You can look at.
It is.
CH, numbers, letters, molecular.
Numbers, letters.
It's molecular. CCl.
All right, let's go over a few of these. Are there any that you guys want to know up here? Are there any that you are confused about and you want to know? Okay, if not, I'm gonna pick out a few. How about this one? This one is a trick one.
Molecular.
This has all nonmetals. This is the one that you have to watch out for. This is called ammonium hydroxide. Ammonium is a cation. Hydroxide is a cation. Or excuse me, this one's a cation. This one's an anion. This one is ionic. Okay, they're both polyatomic ions. This is like the one that you need to watch out for. Okay. That is, yep, and this will come up on Alex, so watch out for that. Okay. How about this one down here? Good, this is ionic. Good. Okay, let's see. How about this one?
Molecular.
Good, this is molecular. Okay, oh, this is, no, that's fine. How about this one? This is molecular still.
Wait, CL? I forgot what it is. Oh, chlorine.
Because this is not one of the ions we have to know. It's not an ion. This is not an ion. This is not a metal. That's covalent. That's molecular.
Wait, so then is it? Wait, I'm kind of confused about. Is
Bro.
Yep.
Is that like? Is that like carbon to oxygen and hydrogen?
Yes.
Oh.
Then why would they use O2?
Because this is the structure of the molecule. That tells. Sometimes the formula tells you about what's there. This is a carboxylate. Yes.
So does that one have like two oxygens?
Yes. Two oxygens. Phil.
So there's ionic bonds that don't involve a metal and a non-metal?
Yes. Ammonium hydroxide is one. That's the one that you will have to know. Yes.
So
Covered.
there's two oxygen, so why isn't it
Yes.
just an O and then a 2?
Because it tells us about the structure. This is like this.
It has.
So sometimes in chapter 13 we'll talk about that.
Okay.
Sometimes if we write it like that, that's telling us more information about the compound.
Okay.
Yeah. You won't have to do that. Okay. Other questions here? We got it? Okay. That's all. Wait, I heard a wait.
Sorry, so for that one?
Yep.
NH4OH.
Uh-huh.
That's just like an exception?
Yes. This is an exception, kind of. Yes. Any other questions? Okay, we are through the notes for today. We have half an hour left of class. I would work on, if you have not done the lab, I would turn the lab in. If you have turned the lab in, double check, make sure that you're happy with your score. You can redo your the ones that you missed, or if you forgot some, you can do that. I will work on grading anything that's been submitted. Then I would work on chapter 3, Alex. And we have lots of time to work on stuff. Okay?
We have 30 minutes.
I'm just gonna draw circles on this pen that I